Hi Year 11, this is our third lesson for the topic of trigonometry. In this lesson we're going to cover radians. So previously we've looked at right-angled trigonometry, including angles of elevation and depression, bearings, 3D applications and exact values. And then last lesson we looked at non-right-angled trigonometry, the sine rule, including the ambiguous case, cosine rule, and area of a triangle. Here's our lesson outline. We're going to look at radians, exact values, length of an arc, area of a sector, and area of a segment. Now we can measure angles in degrees or radians. A degree is a measure of turning, so how much you turn around, whereas a radian is a measure of how far an object has moved on the circumference. So if we have a look at this diagram here, we have the arc length of this circle equal to the radius. And that's the definition of 1 radian. The symbol for radians is C. It's written up a little bit like a power, but it's not always written. So the general rule is if you're given a measurement and it doesn't have a symbol, expect it to be radians because degrees should always be written with the degrees symbol. Let's look at how we convert between degrees and radians. If we take an entire circle, then the angle of turning at the center is 360 degrees, whereas the distance run on the circumference is 2 pi r. Now we said before that 1 radian is when the arc length is equal to the radius. But more simply, we can calculate the number of radians by working out the arc length divided by the radius. So in this case it is 2 pi r divided by r, which is 2 pi. And so 360 degrees is equivalent to 2 pi radians. Divide both sides by 2 and we have this identity. 180 degrees is equivalent to pi radians. So if we want to convert a radian measure to degrees, all we do is substitute 180 degrees for pi. Now if we've got pi on 3 radians, then I'm just going to put 180 degrees in here. And 180 divided by 3 is 60 degrees. So pi on 3 is equal to 60 degrees. How about this one? Substitute 180 for pi. 3 times 180 divided by 5 is 108 degrees. Now, of course, the complication is going to come when we don't have a pi symbol. I can't substitute 180 for pi here. But what we're actually doing is multiplying by 180 on pi. So if you think about it, take this here and multiply by 180 on pi. The pi's cancel out. I end up with 180 on 3. So that's actually what we want to do here. So I'm going to multiply by 180 on pi. I'm going to put this on my calculator using the pi symbol. And that gives me 60.2 degrees. Now if that's a little confusing for you, and it can be tricky, I admit, then here's one way to do it when you don't have a pi symbol. Take your 1.05 and do this. We've multiplied top and bottom by pi, so I haven't changed anything. And now what I want to do is swap this for 180. Now let's go the other way, convert degrees to radians. What we do is write the degrees as a fraction of 180. So I'm going to take my 45 and put it over 180, and then I'm going to put the pi in. Because what we're actually doing this time is multiplying by pi on 180, and you can see that there. Use your calculator to reduce this down. So 45 on 180 is the same as a quarter. So 45 degrees is equal to pi on 4. You will start to recognize these. How about 270? 270 over 180 pi. Use your calculator. This is 3 over 2, so 3 pi on 2. And even something like this, 6.5 degrees, is relatively simple to do. 6.5 over 180 pi. Use your calculator. This reduces down to 13 pi on 360, or you can just give it as a decimal. And you can see how I have included the radian symbol here, but not here. Anything with pi is assumed to be radians. Now, if we want to look up the trig tables in radians on the calculator, then we need to adjust the settings. You can see up the top here that it tells us it's in degrees. To change that, we go Shift Setup and pick 4 for radians. Now it's in radians. So do our first question, sine point 105. Pretty easy. And if you want to put in cos pi on 3, we actually use the pi button, which is there. And there's the answer. Now this is really important. You only need to put your calculator in radians if you're looking up the trig tables. So if you're converting from degrees to radians, you're not looking up sine, cos or tan, so you don't need to change your calculator. We also need to know the exact values when the angles are given in radians. So remember these triangles here? Here's our table. And now we've got 30, which is pi on 6, or 45, which is pi on 4, or 60, which is pi on 3. So let's look at these examples. Write the exact values of tan 60. So start by locating the correct triangle. Tan 60 is opposite over adjacent, so root 3 over 1. Now let's look at radians. Sine pi on 3. So substitute 180 for pi. 180 divided by 3 is 60. So this is sine 60, same triangle. Sine 60 is opposite over hypotenuse, so root 3 on 2. How about cos pi on 4? Substitute your 180 for pi. 180 divided by 4 is 45, so we're up here. Cos 45 is 1 on root 2. And then finally, tan pi on 6, 180 over 6, that's 30, so tan 30. So we're here. It's opposite over adjacent, 1 over root 3. Okay, let's move on to length of an arc and area of a sector. But before we do, let's revise the parts of a circle. So here we have a tangent. It's a line that touches a circle in one position. This is an arc. It's part of the circumference. A sector is bounded by 2 radii and an arc. It's like a piece of pizza or a piece of pie. And here we have a segment. It's like a slice of a circle. It's bounded by a chord and an arc. Now this is a minor segment because it's less than a semicircle. We also need to know the definition of this word subtend, which means to stand upon, because we might get statements like this. The angle theta is subtended by the chord AB. And that means this angle stands upon this chord AB. Okay, so arc length. Recall the formula for the length of an arc in a circle of radius r is L is equal to theta over 360 times 2 pi r. This is the circumference, and this is a proportion of the circumference. Now we just learnt that 360 degrees is the same as 2 pi radians. So let's make that substitution. L is equal to theta over 2 pi times 2 pi r. Can you see how these cancel out? So we end up with L is equal to theta r, which is a much simpler formula than the formula in degrees. Here's an example. Find the arc length and the perimeter of this sector. So we can see that our angle is in radians. It's 2 radians. Our formula is very simple. L is equal to theta r. We just multiply those two numbers. 2 times 3 is 6 centimeters. So that's this length here. If we want the perimeter, we're going to have to add on 3 and add on 3. So the perimeter is 6 plus 3 plus 3, which is 12 centimeters. Now let's look at the area of a sector. Here is the formula for the area of a sector of a circle with radius r if our angle is in degrees. Here's the area of the circle, and this is the proportion of the circle. Again, 360 degrees is the same as 2 pi radians, so let's make that substitution. In this case, only the pi cancels out, but we're left with a is equal to 1/2 theta r squared. Here's an example. Find the area of the sector to 1 decimal place. So we have an angle, 7 pi on 6, and a radius 4 millimeters. Here's our formula. Substitute in 1/2 times 7 pi on 6 times 4 squared, and into the calculator gives us 29.3 millimeters squared. Now, if you were asked to leave your answer in exact form, just put all of these numbers into the calculator without the pi, and then use your fraction button, and you will end up with 28 pi on 3 millimeters squared. Now, we talked before about a segment. It's like a slice of a circle. And if we want to find the area of a segment, then we start by finding the area of a sector. We use that formula we used before. Then we find the area of this triangle. We're going to use a 1/2 AB sine C for that. And then we subtract the area of the triangle from the area of the sector. So here's an example. Find the exact area of the segment highlighted below. So we're going to start by finding the area of the sector. Here's our formula. Theta is pi on 3 and r is 4. And this time we want an exact area, so I'm going to do a 1/2 times 1/3 times 4 squared, which will give me 8 over 3. So it's 8 pi over 3 is the area of the sector. Now let's find the area of this triangle. And we're going to use a 1/2 AB sine C. Now in this case, A and B are both 4 centimeters and C is pi on 3. So substitute in. Because we want an exact area, we're going to use exact values. This is 180 over 3, which is 60. It's sine 60. And sine 60 is root 3 on 2. And tidying that up, we end up with 4 root 3. Now, if you wanted to get an approximate area for this, you would have to put your calculator in radians for this part because we are looking up our trig tables. So there's our area of a sector and our area of a triangle. This shaded part here is going to be the area of the sector. Take away the area of the triangle. And in exact form, that's 8 pi on 3, take away 4 root 3. So here's everything you get on your reference sheet. We have SOHCAHTOA, we have our non-right-angled trig formulae, we have arc length and area of a sector in radians, we have our exact values, triangles, and over here we have arc length and area of a sector in degrees. But you'll see there is no formula for the area of a segment. Okay, that's it. In our next lesson, we're going to look at the unit circle.